Displacement and velocity are important concepts in physics. You might already be familiar with these terms, but in physics they have more precise definitions and maybe a little bit different than you're used to. Let's talk about displacement first. Say I have a train. In order to talk about the position of the train, I'm going to need a coordinate system. Because the train only moves in one direction, I just need one axis. I'm going to use the x-axis. So I'm putting this line down, and it's going to tell us what the position of the train is. The origin is the point where x equals 0. Now, because we want a well-defined position for the train, we're going to just treat the train as a point. So I'm going to take the point to be the front of the train, but it could be anything. Let's start the train at 0. We're going to move the train forward 10 meters and back 5 meters. The train traveled a total distance of 15 meters, but its displacement is 5 meters. Let's use another example. The train goes forward 20 meters. It goes back 25 meters. Then it goes forward another 3 meters. In total, it traveled 28 meters, but its displacement is minus 2 meters. So it doesn't matter how you get there, the displacement is just how much your position has changed by. If x1 is your initial position and x2 is your final position, then your displacement is x2 minus x1. Another way of writing this is writing delta x, or the change in x. For example, if you were to start at 5 meters and end up at 15 meters, your displacement would be 10 meters. Let's talk about average velocity now. We can write it like this. There's an x in the subscript just to remind us that we're talking about the x direction, and the AV stands for average. So to get the average velocity, you take the displacement and you divide it by the amount of time that it took. Here, the t1 is the time that you started at, and t2 is the time that you ended at. For example, let's assume the train started moving at t equals 5 seconds, and its initial position was x equals 2 meters. And it traveled and eventually stopped at 10 seconds, and at the position x equals 12 meters. Then we just substitute these numbers in to the equation for the average velocity, and we would get the average velocity to be 2 meters per second. Looking at the formula again, notice that if x1 was larger than x2, we'd have a negative average velocity, and that's fine, you can have that. A good way to visualize the displacement and the velocity is by making a graph. So let's make a graph. On the vertical axis, we're going to put the position, so that's x, the x coordinate, and on the horizontal axis, we're going to put the time. So let's start our train. Let's assume that it's going to start at t equals 0, and let's also start it at x equals 0, just to make things simple. Okay, so let's start it now. Notice that the displacement can go into the negative too. Let's take a closer look at the graph. I want to calculate the average velocity between the points t equals 1 second and t equals 3 seconds. So let's just label that P1 and P2. So the average velocity is the change in x over the change in time. This may or may not look familiar. What this is actually just the slope of the line from P1 to P2. So remember that slope is the amount that you rise over the amount that you go across in a plot. It turns out that the average velocity between the points P1 and P2 is just the slope between those 2 points. So that means the faster you're going, the higher your velocity is, the steeper this curve should be. And if you're not traveling at all, this would just be a horizontal line. And of course, if you're going in the negative direction, it would have a negative slope. It would be coming down. Let's look at another position versus time graph. But this time we're not going to worry about the acceleration. We're just going to let the train move at constant velocity. By the way, when I say position, I just mean displacement, so I'm using those terms synonymously. Okay, so this train starts, it's moving at a constant velocity, and then it turns back, also at a constant velocity, and then it stays at rest. So here's our x versus t graph. It's pretty simple. There's another graph we can look at as well, which is a velocity versus time graph. So in this example, the first velocity is, well, like I said before, it's a constant velocity. And then the second part, it has a negative velocity. And for the last part, it has zero velocity. It's not moving. So this is what the velocity versus time graph would look like. You're going to be seeing a lot more of these types of graphs. So take a little time to look at them and make sure you fully understand them. That's all for this video. In the next video, we'll work through an example to reinforce these concepts.